by tomorrow?
Will I have the test graded by tomorrow? Odds are pretty good for that, yeah.
Whoa. Whoa, whoa, yeah. Whoa, whoa.
If my son's baseball practice had gone another hour, I would probably already have it graded, but
What's he play?
baseball. I don't think it's clear yet what position he plays. Whatever position they put him in, I guess. But they rotate them around in the practice. Like sometimes he's. I wasn't trying to be funny. I actually just don't know because he hasn't been assigned a position yet, really. But I will begin with a word of prayer. Dearly Father, we thank you for this day. Thank you for these students. Just ask you just bless our work today. Help us to glorify you again, Lord, in what we do. In your name I pray, Lord Jesus. Amen. So we are now at the start of another story arc in this course. And so we're really talking about two-dimensional curves and their calculus. And so in order to do this subject justice, in my opinion, like you really should at least talk a little bit about vectors. All right, so in chapter 10 of Stewart, sections 10.1, 10.2, 10.3, he talks about, parametric curves and so forth and their calculus, but he does so without the vector concept. And I think that doesn't quite do the topic justice, because when we think about curves in two dimensions, we are thinking about x and y together at once. And of course, you've already done that with graphs, right? Y equals a function of x. But the false impression is given sometimes that the parametric viewpoint, like there's this separation. There's the x is a function of t and y is a function of t. And so I want to talk about vectors a little bit in here to try to give you a more manifestly truthful notation for what's going on. And so that's part of the reason I'm talking about vectors at the start of things here. This, of course, is not in Stewart. It's like Stewart does vectors, I don't know, chapter 12 or 13 or something later. All right? So I'm just going to do two-dimensional vectors in here. And so to start with, I need to talk about points. What's a point? Point P, it's got two things, right? P1 and P2. And you could have a point Q, right? You could have Q1, Q2, right? So you talk about the x coordinate and the y coordinate, right? And then if we graph these things, here's your, let's say, P, and here's your Q, right? You can also then talk about PQ. All right, so PQ is a directed line segment. It's a vector which goes from here to there, like this. This is the PQ vector. All right, the formula for this vector is very simple. The formula is Q minus P. So what you do is you do the terminal point minus the base point. That gives you the vector. A vector, again, is a directed line segment. Okay? So let's see here. Now, that makes sense in terms of just the picture, if you want to think about it. If you look at this here, right? And you look at this here, what are these distances here? Well, so in coordinates, what we mean by this, right, is L'angle Q1 minus P1, comma, Q2 minus P2, all right? So this here, these are the coordinates. Listen, so here's my notation, guys. It's pretty simple. I write these sorts of parentheses whatever, for points, these brackets, angle brackets, for vectors. This is more of a conceptual distinction than a mathematical one, because you could add points to vectors meaningfully. All right. anyway, this distance right here, this right here is what? This is P2, excuse me, my bad, Q1 minus P1, right? And this distance here would be what? This is Q2 minus P2, right? That's what those distances are respectively for the points so labeled, right? So what would the length of the vector be? Right, so the length of this PQ vector would be the square root of, you said Q1 minus P1 quantity squared plus Q2 minus P2 quantity squared, right? I'm not really telling you anything new, am I? I'm just maybe giving you a different notation for something you've already talked about. This is the distance formula between 2 points, right? But I'm approaching it to describe how it's something new, which is the length of a vector. It's the length of this directed line segment, all right? So let me talk more about vectors just in the abstract here for a minute. Although not really too abstractly. I want to give you a definition. So let's set aside points for a second, and let's let V be vector 1, and let's let W be vector 2. We can do a couple of basic things to vectors. We can add them, we can subtract them, and we can call what's called scalar multiply them. So what's the definition of addition of vectors? How do you define V plus W? It's very simple. You just add the components. So V1 plus W1, comma, W1 plus, my bad. Man, the board is very, very smudgy today. What's going on up here? So V2 plus W2. All right. So this is how we add vectors. And if you wanted to subtract them, how would you do it? Same song and dance, right? Like that. How do you scalar multiply a vector? So a constant is a scalar. C times V is defined to be CV1, comma CV2. So if you want to, on the flip side of this, if you want to factor a number out of a vector, it has to be present in both components, otherwise you can't pull it out. All right, that's the more interesting aspect of this definition. So this is just the definition. This is how we algebraically add vectors. Now question, what does this mean geometrically? What's the geometric meaning of these rules above? So, very simple. If we draw the first vector, V, as if it's from the origin, all right? So here's V, V1, V2. Right? So I drew that vector as if it's based at the origin, okay? Now I should point out something here. The point right here, right? What is this point? That point is V1, V2. So this is V as a point, if you like. So there's a natural identification with vectors from the origin just to points. And that's why it's reasonable to add vectors to points. All right? Anyway. Now if I draw the vector V2, W, if I draw W as if it's based at V, all right? If I draw W as if it's based at V, then I draw what's called the tail of W, all right, at the tip of V. So here's W, all right? If you look at then what we have all together, we have the sum of v and w as a vector from the origin. Oh man, I was trying to get different. Someone's messed up the caps on the colors of the caps on my markers. It all messed me up. Let's see here. So this right here is the vector v plus w. So this is known as tip-to-tail vector addition. All right. Let's see here. What else can I tell you? What would the meaning of minus? What would minus w look like? Well, let me not do it the same picture. It gets too busy, you know. So if this is vector v, then minus v is right here, right? So minus the vector is what? It is what? It's the same length, right? But opposite direction. Simple example. If I've got a triangle, right? And I draw vectors that correspond to the sides of this triangle tip to tail like this, right? So vector A, vector B, and vector C, right? See how I've got them arranged? A, B, C. What is A plus B plus C in this context? Yeah, it's 0. All right. So I introduced vector length in terms of the directed line segment between 2 points, right? But now we're talking about vectors on their own. They take a life of their own, so to speak. So let me just redo the definition here. Actually, before I do that, let me introduce a new definition, which is the so-called dot product. If we have a vector A, dot product with a vector B, we have A1, B1 plus A2, B2. This is called the dot product of two vectors. All right? The dot product of two vectors. So I'll give you an example of that. If my vector A is, let's say, 1, 2, and my vector B is, let's say, -1, well, let's say -2, comma 4, then A dot B is equal to what? So I do 1 times -2 plus 2 times 4 and that gives me what? I heard a 6. Very good. All right. Let's see here. What is A dot A? What's B dot B? Can you guys tell me? So we get 1 squared plus 2 squared, right? Also known as 5. B dot B, we get -2 squared plus 4 squared, right? Can you guys tell me what the significance of those numbers is? It's the square of their magnitude, or what's, so I don't think I've used that word before yet today, but it's a square of their length, right? So in terms of the notation I have on the other board, this is equal to the length of A squared, and this is equal to the length of B squared, all right? So let me make another definition for us. Definition. If A is not equal to 0, then A is equal to the length of A all right? And we can write that as the square root of A dot A, which is, to be clear, the square root of A1 squared plus A2 squared, all right? So this is the length or magnitude of A. Notice the notation here. We write with the vector is a vector. Without the vector is the length of the vector, which we call the magnitude, all right? And by the way, at the moment, A could be 0, and the magnitude of 0 would be 0. But what I'm about to write doesn't make sense for 0. That's why I've assumed A is not equal to 0 for this definition. The unit vector in the A direction is defined by A hat equals to 1 over A times the A vector. Put a different way, we have that the vector A, right? The vector A is equal to what? So vector A is equal to A times A hat. So A without the vector is the magnitude. A hat is a unit vector that points in the direction of A. So this is why people say a vector is a magnitude times a direction. So this is the magnitude, and this is the direction. It's the direction as a unit vector. Now in 2 dimensions, we have other choices for direction. All right, there are other choices for direction in 2 dimensions, because you can define direction in 2 dimensions. Like if you're on a plane and you're taking direction somewhere, they don't give you a unit vector, right? They give you some sort of bearing in terms of an angle, right? Don't think too much about those. They tend to be measured differently than math. But so this is one of the things I got really confused about when I worked for the Navy, is they like measure angles off the y-axis. It's weird. But here's the standard angle. Let me talk about that. Standard angle. So here it is. If you have vector A, the standard angle for A is the angle that is measured counterclockwise off the positive x-axis to wherever it's going, all right? So, so this is standard angle. So let's see here. If you look at A hat, right? Where is A hat in this picture? Notice that A hat, notice that the vector A is a scalar multiple of A hat, right? So in the picture here, you could draw A hat like this. It's in the same direction. Here I'm assuming that the vector A has a length larger than 1 when I draw that picture, right? The point is that they share the same angle, right? But the difference between, A and A hat is where's this point at? This circle I'm drawing, what kind of circle is it? Right, this is the unit circle. And so that means that you can write A hat in terms of what? Cosine theta, sine theta. All right. So another formula, let me just write it as a theorem, if you will. So the vector A we can write as A hat, all right? But we can also write it as A cosine theta, A sine theta. In other words, A1 is A cosine theta, A2 is A sine theta. And to find the standard angle, you have to solve both of those equations at once, all right? So like, let's go back to example 2. Let's go back to example 2, and let's find the angle for A, and let's find the angle for B. All right? So was this example 4? I lost track. 3? 1, 2. Yeah, okay, 3. Thank you. So let's ask, what is the angle for A? All right. What's the angle for B? Right. Or let me just let me call it theta A and theta B for the sake of discussion. So whenever you're finding standard angles for a vector, you got to be careful, because there's no one trigonometric function that works for everything, right? So let's see here. If I draw it out, what did my A look like, roughly speaking? Which quadrant did it point into? 1, 2. It's in quadrant 1, right? Over 1, up 2. So A looks something like this. And what did my B look like? B was minus 2, 4. So it goes over 2 and up 4. So here's B, right? So let's see here. This one was what? B was what? I've already forgotten. Minus 2, 4, is that right? Okay. So we can figure out what this theta A is. How do we do it? We can just take the inverse tangent, right, of y, which is 2, over the x, which is 1, inverse tangent of 2, right? And that'll be whatever it is. Now, for those of you who are currently in physics, you guys are bored out of your mind at the moment. Feels good, doesn't it? Let's see here, 63.43 degrees. If you're not in physics, maybe this is new to you, and I'm going fast, sorry. The other one, theta B, how do we figure that out? See, to picture it, it's like this, right? This angle is theta B. So if I calculate inverse tangent of 4 over minus 2, what's that tell me? Oh, it's minus 63.43, right? Now that is not the correct angle, right? That is not the standard angle for B. What is that? What is this angle? Where is this actually pointing? Down, right? Yeah, that's actually the exact opposite. It's over here, right? It's actually this guy down here. That would be this angle. This is, 63.43 degrees in the clockwise sense, right? Negative angles are clockwise angles. So I can either, well, anyway, I think I usually put a minus here. I admit there's some, yeah, I think my convention, and I think most people's convention, is to not give meaning to the arrows, because typically people write like double arrows. And the sign is defined to be positive if it's a counterclockwise rotation, and it's negative if it's a clockwise angle. That, I believe, is the general convention here. But anyway, so how do I find theta B? Well, theta B, right, is what? It is 180 degrees minus what? 63.43 degrees, whatever that is. So you got 116.6. All right? So you have to be careful. There's not one formula that works for all 4 quadrants. Inverse tangent will work for vectors in quadrants 1 and 4, but it fails in quadrants 2 and 3. Why? Because the range of inverse tangent goes from plus to minus 90 degrees, right? So plus minus, so like this is 90 degrees straight down here. Minus 90 is the negative y-axis. Plus 90 is the positive y-axis, right? Over here, you've got angles between 90 and 270, right? So theta equals to 0, theta equals to 90, theta equals to 180, theta equals to 270. So this is also what? 360, you know? This is also minus 90 degrees, yeah? This is also minus 180. You see, there are infinitely many choices, right? There's always the degeneracy of the angle. And sometimes we do use negative angles, right? Especially in calculus. Well, even in this course, a little bit later, we're going to be doing, not too long actually, we'll be doing polar coordinates, right? And in polar coordinates, you might have an integration where you want to sweep from, say, quadrant 1 to quadrant 4, right? It would be very awkward to use 0 to 90 and then also to use 270 to 360. Instead, you can just go 90 to minus 90, right? So we do have to allow ourselves this flexibility of using more than one choice of the angle measure, and that's just customary. But technically speaking, that means polar coordinates aren't really a faithful coordinate system, because the real coordinate system, an honest-to-goodness coordinate system, is one that gives a unique pair of coordinates for each point. So the polar coordinate system fails in 2 regards to do that. One is at the origin. The origin has no angle, it's not defined. And the other is this 360-degree degeneracy of our angle. We can remove the degeneracy by just removing a ray from the discussion. But okay, anyway. Next theorem. The dot product has a wonderful formula. A dot B is equal to AB, cosine of the angle between them. So here, the picture is this. Here's your B, here's your A, this angle is theta. This is not a trivial theorem. This theorem is logically equivalent to the law of cosines. Law of cosines is kind of a heavy hitter, right? It's not a particularly easy thing to prove. It does require some effort to prove that. I have made it a homework problem for Calculus 1 in past years. But anyway, we're just going to take this as a fact for here. I might have time in Calculus 3 to prove this, but I'm just going to, for here it's going to be dropped from the sky. All right, this is true. Yeah.
You made Calc 1 prove the thing that you just said was like super difficult with it.
Well, yeah, but Calc 1 is closer to, you know, like basic trigonometry. At the start of the course, you know, as a trigonometry review, derive the law of cosines, yeah.
You're a villain.
I'm a villain? Thanks.
Very least anti-hero.
I'm not the villain that you need, I'm the villain that you want.
Ooh, precisely.
Okay, I don't know, I'm just making garbage up now, but anyway. I don't know, they used to have like a fan book, well, back when you guys used Facebook, which is like, wow, right? But when I, first couple of years I was teaching, there was somebody had a fan page for me on Facebook, and they would collect quotes. I don't even remember saying half this stuff, you know? But apparently at the start of physics, I once told the class that, you know, and this is back when I used the book more litigiously, I told them that not having their book at the start of class to study, it would be sort of like, I don't know, going to the edge of a desert, taking your chainsaw, cutting your legs off right below the knees, and then starting to walk. This is, yeah, that's what I said. Like, I don't know the context of all this, but this is something I said apparently.
We can make you an Instagram page.
An Instagram page?
Yeah. TikTok.
Oh, I don't think I'm ready for it.
You don't have to know about it.
Okay, so this,
YouTube in the bio.
let's apply this formula to example 2. So here's example 4. Find angle between A and D. All right. And I probably should find the unit vectors for A and B while we're at it, right? Because I haven't done that yet. So let's see here. We have A dot B equals to AB. Cosine of the angle we don't know, all right? Now this theta is not a standard angle either, right? This is the angle between the vectors, okay? It may or may not be a standard angle, whatever. A dot B we calculated before, it was 6, right? What's A? A is the length, it's the magnitude, it's the square root of 5. What's the length of B? Well, it's the square root of B dot B, which is square root of 20. What is cosine? Well, cosine of the angle we don't know, right? So how do you find theta? This simplifies, doesn't it? That's the square root of 100, which is 10. So we've got 6 over 10, also known as 3/5. This does not matter. But then that gives us theta is inverse cosine of 3/5. Good news, we don't need to draw a picture. This is true. This is not like my use of inverse tangent over here. You have to think, you have to draw the picture to figure out standard angle. To find the angle between two vectors, this dot product formula is always legit. And it always gives us an angle between what? What does inverse cosine tell you? What kind of angles? Oh, cool, my calculator doesn't need the parenthesis. I didn't close the parenthesis on my cosine, it still figured it out. Good job, programmer of this calculator. Let's see here, whoever you are, 53.13 degrees. I mean, this guy, I've had this calculator for a while. He's probably dead. I don't know. Is that too dark? No. He gamed too long. He didn't stop gaming for 3 days and he died. That was his fate. You know, something like that. Okay, so 53.13 degrees is the angle between these vectors. Does that make sense, by the way?
Yes.
Can you see it? So what is the difference of 116.6 degrees and 63.43 degrees? Should be that, right? Because if I take this angle minus that angle, I should have the angle between them. Did it work? Okay, cool. Find A hat and B hat. This is going to be kind of anticlimactic. A hat, it's 1 over A times A vector. What's that here? 1 over the square root of 5 times, I'm still using the same A, 1, 2, right? And B hat, 1 over B times B vector, 1 over the what? Square root of 20 times minus 2, 4. And of course, we could do better. So that would be what? 1 over root 5. Well, I don't know. See, I said we can do better. Actually, I'm not so sure. I'm inclined to count both of the answers that I have on the board as correct. And also, if you want to simplify these in terms of decimals, I'm also sympathetic to that. In fact, not only am I sympathetic to it, I demand it in physics, because I don't want to grade that in physics. All right. Any questions? Good. So these are vectors. Let us talk about, so I think the first 4, maybe 5 problems in your homework are just this stuff. You should be able to do these problems now, right? So try to do them. If I have inadvertently missed a concept, ask me about it next class, okay? So now I want to talk about curves. two viewpoints. What's that?
For a second, I thought you said curves, 2 bonus points.
Oh, two bonus points. No. I'm not done grading the test yet, so talk about that later. But so circle. What's the equation for a circle? X squared. Well, let's say. Well, let me be a little bit more adventurous. X minus x naught squared, right? Plus y minus y naught squared equals to r squared. All right. This is, I would view this as the implicit viewpoint. Implicit viewpoint in the sense of the interrelation of x and y, they're all intertwangled in some equation, right? But you've studied this before, right? This is a circle, radius r, centered at x naught, y naught, right? The explicit viewpoint, also known as the parametric viewpoint, all right, it instead tells you what x and what y are for the circle directly in terms of a new thing we call a parameter. So here, parametric equations are like this: x equals to x naught plus r, let's say, cosine t, y equals to y naught plus r sine t, where 0, let's say, is less than or equal to t, is less than or equal to 2 pi. Another one, y equals mx plus b. Now, I say that that's the implicit viewpoint, but now we're kind of cutting. I don't know. Is it really the implicit viewpoint? To make it the implicit viewpoint, maybe I should do something like rewrite this as, 0. Well, I'm going to leave it like this, but maybe I should rewrite it as an equation equal to 0 to really be. I would say that graphs of functions are kind of in between worlds, because they're, on the one hand, an equation involving the Cartesian coordinates, but on the other hand, they're explicitly telling you what y is as a function of x, right? So if you're talking about, this is a graph of a function, right? So in this context, you could do this: x equals to t, y equals to, mt plus b. For what? For t in the reals. Another viewpoint, another example. X squared minus y squared equals to 1. Do you guys know what this is? This is a hyperbola, right? What is the parameterization of a hyperbola? Well, we could do this. X equals hyperbolic cosine of t, y equals to hyperbolic sine of t, and here t is any real number. Now you might say, well, what do vectors have to do with this, right? Well, let me try to explain a little bit. Yep.
Where are you pulling the t from?
Ah, where's the t coming from? That is a good question. The answer is my imagination. The answer is t is not unique. T is a parameter. We're introducing t. Let me try to give a picture of what's going on here. Do it over here. So let me be a little bit more abstract for just a second, rather than these examples. Let me just kind of give you a generic snapshot here. So suppose we get, and I'm going to answer your question, kind of, sort of. But see, a curve, it could be any old thing, right? A curve could be something like this. All right? See, a curve, right? And on the one hand, you could explain this curve, perhaps you could find an equation. Let's say f of x comma y equals to 0. So if you can solution set is C. All right? That's the one thing. What is t? Well, if you could imagine a rule, right, where you start at some point on the curve, let's say here. Let me use a different color. Like here, right? Maybe that's t equals to 0, right? And then I choose a direction along the curve, being positive. And then maybe t could be the arc length. That's one idea. So you could say this is arc length 0, and if I go over to, if I go 1 unit further along here, then you've got, you know, t equals to 1. If I'm thinking of t being arc length, although I usually use an s if I'm thinking of arc length. I usually use t if I'm thinking of time. So we could be thinking about this curve as actually a physical trajectory of some particle. And this is where the particle is at time 0. This is where the particle is at time 1. Over here is maybe where the particle is at time 2, and so forth, right? And so I can also describe this curve in terms of a mapping we call the position. So another way to describe C is like this. R is a mapping from, let's say, you know, t naught. Well, I don't know. I use some from some I. I is some subset of the reals, all right, to R2. Some interval of real numbers. So that I could be, it could be the whole real line. For my circle example, I was 0 to 2 pi. All right? And here, R, the curve, is actually literally equal to the image of that set under the map. Let me be more explicit here. R of time t is equal to what we typically denote by x of t, y of t. So what does it take in the abstract for this to be a parameterization of this curve? What does it mean? It means that you can take these equations, these formulas for t, and you can plug them into the equation over here, and they work. All right? If you look at my 3 examples, that's true. If I take these formulas, right, and I plug them in here, I get r squared cosine plus r squared sine squared, which is sine squared plus cosine squared being 1. You get r squared equals r squared. It works, right? If I plug these into here, it's obvious that I get y equals mx plus b works when I plug these in, right? Because the t's cancel, and you can see the equation's true. When I plug cosh and sinh into this equation, well, that's the identity for cosh and sinh, right? So it works. But I think of these parametric equations, as Stuart calls these parametric equations, I think of them as a package deal. So like calling this 1, calling this 2, calling this 3. For 1, I have r1 of t equal to x naught plus r cosine t, y naught plus r sine t, okay? For 2, I have t, mt plus b. That's my parameterization as a vector. So I talk about the vector parameterization versus the parametric equations. Don't be frightened by this terminology. There's really not much to it other than just grouping both of the equations as a map. So this is what we're interested in studying. Sorry, I'm over. We're interested in studying the calculus of these kinds of things. These are called paths. So we need to understand the calculus of these paths and understand how that then reflects on the underlying geometry of these curves. That's what we're up to next. So see you tomorrow.